Section 6.4, conservative versus non-conservative forces. We're going to make a distinction here between two different types of forces. And the advantage will be that if we're able to identify forces are conservative, we'll see in the next section that we have a really powerful analysis technique that we can use. If there are non-conservative forces present, that's also really useful to be able to identify because we'll need a different problem-solving technique. So that's why we want to be able to distinguish between them. That will tell us what types of equations to use when solving a problem. So first, what does it mean to be a conservative force? Well, there's two different ways of looking at it, and both are equally true. One version of the definition is that a force is conservative when the work it does on a moving object is independent of the path between the object's initial and final positions. Let's look at this and come back to version 2. So this we saw with our ball example, right? The work done by the force of gravity was independent of the path between the initial and final positions. The work done by gravity will be the same if the ball travels straight down or if it goes any other path to go between the same initial and final positions, which only depend on the height. So if the path doesn't matter, that's a sign that our force is conservative and that the gravitational force is a conservative force. The other version we have is that a force is conservative when it does no work on an object moving around a closed path, which means starting and finishing at the same point. This also can be shown with the work done by gravity. So if we consider a roller coaster, because I like roller coasters, you could look at the work done by gravity as the roller coaster starts at the top of the hill and goes down the hill. As it's going down the hill, the displacement is in the same direction as the force of gravity. It's doing positive work, and that's why the roller coaster speeds up down towards the bottom of the hill, right? Woo! Lots of fun. So positive work is being done, but you don't just stay at the bottom, right? Eventually, you go up and down and up and down and up and down, and anytime you are going up, your displacement is now opposite the direction of the force of gravity. So the force of gravity is now doing negative work, slowing you down. That's why as you go up the hill, you're going to naturally slow down. Most true with the big hill at the end, going up it, you're going to have less and less speed or velocity because gravity is now doing negative work to slow you down. And it turns out it balances out just right. If you get right back up to the same start point, all of the positive work done by gravity is exactly counterbalanced by the negative work done by gravity. You can plug in the initial height and the final height are both the same. So if you subtract them from each other, you get the work done by gravity is 0. No net work is done moving around this closed path. So both of these definitions illustrate how the force of gravity is a conservative force. There are a couple of other conservative forces that you will see. So let's take a look at those. So the gravitational force is one. Later on this semester, we'll see the elastic spring force. Anytime you have a spring, turns out that force is conservative. And then if you take physics 2b, you'll get a chance to see that the electric force is also a conservative force. So that won't be this semester, but if you stick around next semester. What about non-conservative forces? Non-conservative forces are basically any other force out there. So friction is one example, or air resistance, which is very similar to friction. And these can be illustrated by how they do not follow both versions of the definition of a conservative force, right? If you imagine moving between 2 points, and if you take the shortest distance between the 2 points, versus if you take a longer path to go between those same points, you're not going to get the same amount of work done by friction, because friction is going to keep doing negative work. And if it has longer to do that negative work, it's just going to do even more work. Similarly, you can't somehow go around a closed path and end up with 0 work, because friction will always do a negative work. You can't somehow turn friction around so that it does positive work and adds kinetic energy back to your system. Friction will always be pulling kinetic energy out of the system. So hopefully that helps to highlight that. You can just always think of friction as a non-conservative force. Air resistance, if it's mentioned, is one. Tension will be a non-conservative force that plays a role when it is along the motion. The normal force is a non-conservative force, but it often ends up not being a factor because the normal force is often perpendicular to the displacement. So if it is perpendicular to the displacement, then it's not a big deal. Propulsion force of a rocket is another example of a non-conservative force. So good to have a sense of what non-conservative versus our conservative forces are. And so if we want to think of the work done by these forces, a lot of times there's work done by the conservative forces, like the work done by gravity, but there also might be work done by the tension, right? Pulling a block along the slope. So the net work, the total work, is going to be the work done by the conservative forces plus whatever work is done by the non-conservative forces. And we can remember our previous relationships with work. We saw that the overall work is related to the change in kinetic energy. That's part of why this equation is so powerful of work is equal to change in kinetic energy, because that is just total work. It's not specific to conservative or non-conservative. Pretty convenient. The change in potential energy that we saw with the work done by gravity is only equal to the work done by conservative forces. We derived this with gravity. Potential energy is only going to apply, it's only a concept that works with conservative forces. And then we have the work done by non-conservative forces. So if we fill in this delta KE and negative delta PE into this equation, then we can get a work energy theorem overall, right? We have delta KE is equal to negative PE plus the work done by non-conservative forces. So I'll add my delta PE to the other side. And this tells us that the net work that is done by non-conservative forces only, so not anything done by gravity, is equal to the change in kinetic energy plus the change in gravitational potential energy. So there are some problems out there where they just tell you straight up, the work done by non-conservative forces is blank, or the non-conservative force is this amount over this displacement. You can figure out the work done by that non-conservative force, and that will tell you the change in kinetic energy and the change in potential energy, which are the forms of energy we often really want to hone in on and understand. We'll also see in the next section what happens when there's no work done by non-conservative forces, and that brings about an even better result. So stay tuned, stick around for that.